So I'm going to do a talk through for 3.3, the homework. Making use of energy. I've got the formula sheet here, but these things don't come with a formula sheet, but I'm going to try and sort that out for next year. So here's the first one on density. People wants to find the density of oil. She uses chemical balance and she places the empty. So she's taking the mass of the empty container, which is 112. And then she's going to put the liquid in. She pours some oil. And then that measures 75, look at it. And it weighs, or I should say the mass is now 172. So the next question now is a 6 marker. It says, use the data to find the density of the oil. Use an equation from page 2, which is this page, and show all your work and explain each stage of the calculation. So I haven't explained it, but I will explain each stage of the calculation as I talk through it. So the first thing was the mass of the measuring cylinder was 112, as you can see from the first page. So we needed to take that first in order to get the mass of the volume on its own, of the oil on its own, sorry. So once we put the oil in and we fill it to 75, we know it weighs, or the mass is 172. So I've said there that the measuring cylinder plus the liquid is 172. Therefore, the mass of the liquid is going to be the cylinder and the liquid minus the cylinder. So 172 minus 112. So the liquid, or the oil in this case, has got a mass of 60 grams. It's got a volume of 75. Now that we know that, we can use an equation from page 2, which is going to be this one here. So density, mass, volume. So this is the symbol rho, and then mass over volume there. Now, because this mass is on top already of something, mass stays at the top, and then rho moves down. So this density moves down. Remember, if they're together, that means they're times. So P would push up in a triangle. This would push up in a triangle. But now, something's already on the top of something, so that stays on top of the triangle. So I haven't actually drawn, yes I have, I've done the triangle there, look. So M stays on top, it's already on top of V, and then the density comes down. So density, if we cover your finger over it, equals the mass over volume. So this time it's going to be 60 over 75. And that's going to come out to 0.8 grams per centimetre cubed. Where did I get this from? Because usually density is in kilograms per metre cubed. Well, I'll tell you where I got it from. We're working in grams, so you're going to have grams there. And we're working in centimetres cubed, so centimetres cubed there. So you don't need to convert all that now to kilograms per metre cubed. You can just leave it like that, because that is accurate. And the other way you could think about it is, I've got mass, which is grams, over slash volume, which is centimetres cubed. And that's what basically that means, grams per centimetre cubed, mass per volume. The last bit of this question, state 2 ways in which the density of the oil could be found to a greater accuracy. So how can you improve that, the practical really? Well, you can get a better resolution. Think back to when you did your practical investigation. Resolution is pretty much the increments that everything goes up in. So on a measuring cylinder, it goes up in ones. Well, you can improve that, just get smaller increments, and then you're going to have more accuracy. And if you take repeat readings with different volumes of oil, you're going to get more of an accurate reading there. I think this is the next question. Actually, I just had a look. It's part of the same question. So you got a wind turbine and a tidal water turbine. There's no question on this page, so the questions come in this. Calculate the difference in power output between the two types of turbines. So the power output is power output there. So the tidal is 2.9 and the wind turbine is 1.5. So literally the difference is just the small one take away, the big one take away the small one there. So we've got 1.4 megavolts. And if we just look at the front there, there's your mega. So it's going to be 1 with 6 zeros, so that's 1 million. But I got the units from there, look, just in case you were wondering, megavolts. And there's a mark for megavolts. Oh, but actually, this 1.4 megavolts is worth the mark. State one reason why water turbines have a bigger output than wind. Well, let's have a look at the table. Density of water is massive there. Okay, so I would say density is greater. And that's what I've said, density is bigger. Other than having a large power output, explain one advantage that tidal water turbines have over wind turbines. Well, water turbines are smaller and cheaper. Is that what I've got that? So, no, there's no price in this. So this is just prior knowledge you need to know. And less harmful to wildlife because they're below the water and they're out of sight. So there's no visual pollution then. And I think that is it for that question. Yeah, we go on to homework 2 then. So homework 2, the following table gives information about 4 metals that's used overhead in the national grid. So we got copper, steel, aluminium, lead, all with different strengths. You can see steel there is the strongest. You can see copper has got the ability to conduct electricity the best. And then density, the lead is massive on the density scale. Use the information table to answer the below questions. Give one reason why copper is usually the best metal to conduct electricity wires. Because it's the best conductor of electricity in the table. You can see that. It's got what is called as, well, all metals have free electrons, so these delocalized electrons able to carry the charge. Name a metal that would be most unsuitable for overhead cables. It's going to be lead because it's massive on density there. Okay. It'll be heavy. Explain why actual overhead cables are made from thin steel core. So you've got really thin steel core there, surrounded by aluminium. Well, steel is very strong. You can see from the table its strength is 800 to 2,000 units. And aluminium is low density, it's very light. So I'm going to use aluminium because I'm not going to use copper because its density is too high. So I'm going to use the lightest material there. And it still kind of conducts, it's still going to conduct electricity, whereas lead doesn't at all, really. Aluminium used in a 100 meter length of cable has a volume of 0.12 meters cubed. Use an equation, mass equals density times volume. And the information from the table opposite to calculate the mass of the aluminium in the cable. So let's go look at the mass. We need the volume, which we've got from here. And we need the density from the table. So from the table, you can see the density is, for aluminium, 2700. And that's why I've got it there, 2700 kilograms per meter cubed. And then I do the calculation, and it comes out to be 324 kilograms, because we're working in kilograms this time. And then we're on to we're on to homework 3 now. Classroom has volume of 80 meters cubed and contains 104 kilograms of air. Use an equation from page 2. Well, we kind of know the equation now, don't we? To calculate the density, it's going to be this triangle here. I know my V, I know my M. So rho equals M over V, and that's your answer. 1.3 kilograms per meter cubed. And you get a mark for stating the unit there. Classroom is now heated by a radiator, and it sets up a convection current. So convection currents, as we know, hot air rises and displaces the cooler air because they get less dense. When particles have energy, they become more active, more kinetic energy, so they're going to try and take up more space. And in a gas, that is, there's no fixed volume, is there, apart from the classroom, which is 80 meters cubed. So this gas is going to spread out, and the more spread out it becomes, the less dense it becomes, and that's why it moves up top. But it will eventually cool and come back down. That's why it's called a current. It keeps, it's like a cycle. And there's your radiator. At which point A, B, or C is the air in the classroom. The hottest is going to be A, and the less dense is going to be A there. Give a reason for your answer because hot air rises and expands. And then part C, a shiny silver coated sheet of plastic bubble wrap is placed on the wall behind a radiator or the radiator. Explain how this can reduce heat loss from the classroom by conduction, convection, and radiation. So that's the 3 types of heat transfer there. Well, I've said the silver sheet is going to reflect infrared. Do you remember infrared from the EM spectrum? Just below visible light. It's going to reflect infrared radiation back into the radiator. So the radiators, so there's usually a thermostat. When radiator becomes cooler, it'll kick in again. But if it's being reflected back in, then it doesn't require it to be heated so much. And it's also going to reflect, it's going to kick some heat back into the room because it's going to reflect that in because it's shiny. So it's an excellent reflector and not a good absorber. Remember, black surfaces are good absorbers, which is why if you've got a black t-shirt on a hot day, you're going to get hotter than if you've got a white shiny because it's going to reflect some of that sunlight off. Then the bubble wrap is going to, also in this case, you'll see when people run a marathon, they're going to wear these sort of cloaks of silver sheeting. It's going to reflect heat back into their body. It stops them losing heat quickly. So another sort of link there. The bubble wrap is going to trap... sorry, my phone's ringing a minute. Right, so where was I? I think we did the first point, and we're coming up to the bubble wrap now. The fact that it's sort of padded and packed like that, it's got the ability to trap pockets of warm air there from the radiator, which is going to reduce heat loss via conduction because there's already, so if there's warm air there, it's already been warmed, so it doesn't need to be warmed via conduction anymore. So it's going to reduce that. It's going to reduce that conduction. I've said plastic is also a good insulator, which it is. So anything that's a good conductor. So if you had, for example, this radiator, if you had metal touching the wall, and let's just say the wall was made of metal, metal is a really good conductor of heat and electricity, so that heat's just going to disperse, and it's constantly going to be drawing heat out of this radiator. Whereas if you use plastic is a poor conductor, it's a good insulator. Therefore, again, you're going to reduce heat loss via conduction and convection when it's because you've already got, especially if it's this bubble wrap, you've already got those pockets of warm air. And the last point I've made, I know there's only sort of 4 points for 6 marks here, but some of these are backed up with a little bit of explanation. The outside air temperature of the wall, which is outside, is going to be reduced by both factors above. So what that really means is convection is going to get reduced as well. But even if you get the first 2 points in, you're looking for good marks there. It's a difficult question because there's not much you can get for 6 marks, not many points you can make. And then we come to homework 4. I think we're going to stop the video there and do part 2. So I'm just going to write